A scientist fires light at a single electron. The instant it hits, the electron doesn't just move. It literally disappears. And this happens every single time. The very act of looking destroys the information you're trying to find. Think about that. We've decoded DNA. We can detect gravitational waves from colliding black holes a billion light years away. But we cannot, and I mean cannot, take a simple picture of an electron without making it disappear. So why does the universe work this way? And what happens when we trigger it too hard? For centuries, humans believed in a simple promise. Build a better ruler, and you can measure anything perfectly. The universe was like a giant clockwork. If we knew all the gears and their positions and speeds, nothing would be beyond prediction. No location too small, no speed too subtle. We were certain that uncertainty was just ignorance waiting for a better instrument. Then, in 1927, that certainty shattered. A young physicist named Werner Heisenberg made a bold claim. There is a fundamental limit to how precisely we can know nature. No matter how advanced our tools become, some uncertainties can never be squeezed to zero. This idea felt like a violation of the scientific dream, but experiments proved it true, again and again. But wait, it gets stranger. Because this isn't just about tiny particles, it's about you. Here's the mind-blowing Heisenberg Uncertainty Principle. The more precisely you pin down one property of a particle, the more another property blurs out. Pinpoint an electron's position to the tiniest fraction of an atom, and its momentum, mass multiplied by speed, becomes wildly uncertain. Measure its momentum exactly, and its position smears into a probabilistic cloud. It's as if the universe says, you can have one measurement, not both. And if you think that's weird, we're just getting started. Hit subscribe, because what comes next makes this look normal. Why would the universe have such a strange rule? A part of the answer is, to measure something, you have to disturb it. At the quantum scale, seeing isn't a gentle glance. It's a physical confrontation. Visible light, say a soft red glow, is far too large in wavelength to even reveal an electron. So we switch to a fierce, tiny wavelength photon, perhaps an intense blue, ultraviolet beam. Now we can hit the electron and get a glimpse, but that high-energy photon blows the electron out of place, like a cue ball scattering an unlucky marble. Try using a weaker, gentler light to disturb it less, and the electron stays put. Yet then, we hardly see it at all. Nature gives us no win-win. But that's not even the weirdest part. Watch what happens when we try to measure something bigger. This isn't just theory. It's been demonstrated. For a 0.14 kilograms, about 5 ounces, baseball cruising at 120 meters per second, we could in principle know its position with absurd precision, uncertainty on the order of 100 non-illionth meters, a decimal point, 31 zeros, and then a 1, far smaller than a single atom. Virtually perfect. So far, so good. Nothing strange here. Until you take an electron moving at the same speed and try to measure it as precisely. Its position might come out uncertain by around 1.5 millimeters. In other words, the electron's location would be a fuzzy region bigger than a grain of sand, just from quantum jitter. That electron is roughly 1029 times more uncertain in position than the heavy baseball. That's like knowing a baseball's location down to a space smaller than the smallest virus, while the electron's position is as fuzzy as a whole grain of sand. But here's where it gets weird. At the tiniest scales, then, uncertainty isn't tiny at all. It's a brick wall. This principle upended science's comfortable clockwork picture. It means that on a fundamental level, nature keeps secrets. We can never know all the details at once. But here's the thing. This isn't just about tiny particles doing weird stuff. It's about the universe having a speed limit for knowledge itself. And when scientists tried to break that limit, well, they discovered 3 ways to try. The third one literally broke physics. Let's imagine we don't take uncertainty for an answer. Scientists have tried to outsmart nature's limit in increasingly ingenious ways. First, the sneaky observation. Set up an experiment to watch a particle without disturbing it too much. For example, fire a beam of electrons through 2 tiny slits and observe how they land on a screen. If we don't peek at them in transit, they act like waves, creating a striped interference pattern. Beautiful, right? Now, watch what happens when we get greedy for information. The moment we measure which slit each electron goes through, the magic disappears. The interference pattern collapses. Now electrons hit the screen in simple stripes, as if they knew we were watching. In trying to pin down their path, we destroyed the very phenomenon we hoped to measure. It's like the act of observation forced the electron to make a choice, and we lost the richer truth of its wave-like behavior. We get certainty about the path, but at the cost of losing the bigger picture. Frustrating, right? Then something happened that nobody expected. We up the ante with technology. If direct observation fails, how about using sheer precision to our advantage? In our best labs, scientists cool atoms to near absolute zero and use ultra-stable lasers and fancy quantum tricks to measure beyond normal limits. They even found ways to squeeze uncertainty, literally trading off precision in one measurement to gain more in another. For instance, by accepting more uncertainty in timing, researchers can measure distance a bit more accurately than the standard quantum limit, but not beating what Heisenberg's rule would normally allow. It's like tightening one end of a balloon. The other end bulges out, but at least one side gets slimmer. Using this cheat, we built something impossible. Devices like LIGO, which detects gravitational waves by measuring mirror positions to within 10 quintillionth meters, that is a decimal point, 18 zeros, and then a 1, manage to sense incredibly tiny disturbances. LIGO can detect a wobble smaller than a proton. That's like measuring the distance to the nearest star and being off by the width of a human hair. Impressive, right? But watch what happens when we turn the energy dial all the way up, when we fire so much power at one tiny spot that space itself starts to crack. Use huge energy to pinpoint a particle's position ultra exactly. Build a mad scientist machine that concentrates energy into a ridiculously small space to probe nature's tiniest details. And for a moment, it might seem we're getting somewhere. We're probing dimensions a million times smaller than an atom. In 1999, physicist Leonard Susskind was having dinner with Stephen Hawking when they realized something terrifying. Susskind later said his fork stopped halfway to his mouth as the implication hit them both. That concentration of energy spawns a tiny black hole and swallows the measurement whole. No, this isn't science fiction. At scales around 10 to the minus 35 meters, the Planck length, any attempt to measure position more sharply makes space-time itself rattle and fold. Gravity becomes dominant and creates a minuscule black hole, erasing the very information we wanted. The universe nullifies our experiment. It's the ultimate disappointment, nature's keep out sign at the door of the infinitesimally small. After these escalating tricks, we find ourselves at a cliff's edge. Every strategy, clever observation, high-tech precision, brute force energy, has failed to break the uncertainty barrier. So scientists did something nobody expected. They stopped trying to break the rules and started building with them. And that's when everything changed. What they discovered next powers the device you're watching this on right now. Hitting the quantum uncertainty wall could have felt like a dead end. But instead, it opened a new path. If we couldn't beat this limit, we embraced it. Physicists built a whole new kind of science on uncertainty's terms, quantum mechanics. Instead of trying to know exactly where an electron is or how fast it's going, we speak in probabilities, a spread of possible positions, speeds, energies. And when we do, the universe suddenly makes sense again. By accepting a bit of fuzziness, our equations started predicting how atoms behave with spectacular accuracy. In fact, quantum theory nailed predictions like the electron's behavior to within less than 1 part in a trillion. And this fuzzy theory powers real technology, from the chips in our smartphones to lasers and MRI machines. Embracing uncertainty opened the quantum era of human progress. So, why will you never measure something perfectly? Because at a fundamental level, nature doesn't have perfectly definite things to measure. An electron isn't a little marble sitting in one exact spot with one exact speed. It's a blurry wave of possibilities until we observe it. The uncertainty principle isn't a bug. It's a feature of a universe built on waves and probabilities. Think about it. Without quantum uncertainty, atoms couldn't exist. Stars wouldn't shine. Your DNA wouldn't work. That annoying blur at the quantum scale, it's the reason you exist. We took nature's blurry pixels and built lasers, computer chips, and MRI machines from them. But here's the kicker. Some scientists think we're still missing the big picture. What if particles aren't dots at all? What if they're tiny vibrating strings, and uncertainty is just the sound of the universe humming? Could there be a level beneath quantum physics, a new story that makes sense of the chaos? Many scientists believe there is. Some propose that every particle is a tiny vibrating string, and that what we perceive as uncertainty is just the twanging of these fundamental strings beyond our resolution. String theory is one audacious attempt to unite quantum physics with gravity and explain why the cosmos has this built-in fuzziness. In the end, the universe hides absolute knowledge behind uncertainty, ensuring we never run out of wonder to explore.